Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to use the limit process to basically turn an area estimate into an exact area. So what we're going to do here is we're going to try to calculate the exact area under the curve y equals x squared from 0 to 4. Now, in my previous video about estimating errors, I talked about how different rectangle setups will yield different types of estimates. So here's what I mean. If I set the rectangles up like this, then what's going to happen is we're including areas here that aren't actually under the curve, and that gives you what's called an upper bound estimate. I'm going to do the next one in green here. If I set the rectangles up like this one actually is like a 0 there, that's going to give me a lower bound estimate. And what I did in my previous videos is I used the midpoint formula, setting the rectangles up like the ones I have in red. That gave me kind of the best estimate using a finite number of rectangles. Now in the previous video I was only using 4 rectangles. There's an important thing to realize is this, that the estimates, all of them get better and better and better for larger values of n. So the upper bound estimate, the lower bound estimate, and the midpoint should all basically converge to the same value if n is large. 20 rectangles, 100 rectangles, 1,000 rectangles, and so forth. And there's real no limit to how many rectangles we can use. So what we're going to do here is instead of choosing an actual numerical value like 4 rectangles like I did in my previous video, we're going to leave this kind of blank here, kind of arbitrary. We're going to set up an estimate for the area, and then we'll use the limit process to drive our estimate to perfection basically. So here's what that might look like. If we leave this blank, or not blank, but I'll say variable here, n, the number of rectangles, the delta x is still given by b minus a over n. In this example, a is 0, the upper bound b is 4, so the delta x is equal to 4 over n. Now if we had, say, 4 rectangles, the delta x would be 4 over 4, which would be 1. Or if I used 10 rectangles, the delta x would be 0.4. What I'm going to do is I'm going to leave this as a variable, and later in the problem drive that variable to infinity. Okay, so now the setup here. Now, before I tended to use the midpoint formula. I'm not going to bother with the midpoint formula here, and I'll kind of explain why in just a minute here. I'm just going to draw them with an upper bound estimate. And the reason for doing that is this. Now what I need are these x values here. Whoops, let me do this in red. Red here, and the next one I need is here, and the next one I need is here, and so forth. Notice that this is the first rectangle, and this x value is equal to delta x, or let's call it 1 times delta x for a moment. This x value, now you see that it's delta x from here to here, and another delta x from here to here is 2 delta x. The third one is 3 delta x, and so forth. So in general here, I can write a little formula that says this. X sub I, which is the x value I need for the ith rectangle, is equal to I times delta x. Or in this case, 4i over n, because delta x is 4 over n. So what I've done now is I've made myself a little formula here to give me the x values that I need at the right-hand side of every rectangle. Now, I could have also used the midpoint rule here, no problem. It's just that if I use this right-hand type of rectangle like I did, the x sub i's are really easy to calculate. And I know that if you use a large value of n, the upper bound estimate, the midpoint, and the upper bound and the lower bound estimate will all converge to the same value anyway. Right? So here what I have is a little formula that tells me the x value at the right hand side of any rectangle I choose. So for example, if I wanted the 50th rectangle. 4 times 50 over n would give me the x-coordinate at the right-hand side of that rectangle. Now, the area here for the ith rectangle, that can be any of them, is equal to the function value at the appropriate place, so I'm going to call that f of x sub I, times the width of each rectangle, which is delta x. This is true for any rectangle. For the first rectangle, the 5th rectangle, the 100 millionth rectangle. It's true for all of them. Now, f of x sub I, since our function is equal to x squared, f of x sub I is equal to 4i over n squared. And then the delta x is equal to 4 over n. This now gives me a formula that will tell me the area of any rectangle I choose. So for example, if I is 3, the area of the third rectangle is 4 times 3 over n, the quantity squared, times 4 over n, for any given value of n. What we want now is the total area. The total area is going to be approximately equal to the sum of all of these, where I starts at 1 and ends at the total number of rectangles, which is n. So we need to calculate the sum of the quantity 4i over n squared times 4 over n. So here is a formula now that will estimate the area bound under the curve. I'll take a moment to save this. All right, so now we got to figure out, what this thing is, or how do we calculate it? I don't need this stuff anymore, so I'm going to make myself a little more room. Let's put this up here. Okay, so now calculating this thing. Actually, need a little more room yet. Oops. All right. So this is going to be approximately equal to the sum I equals 1, 2, and n. All right, so let's kind of separate stuff off here a little bit. 4 squared is 16 times 4 is 64. N squared and another n is n cubed, and then I squared. Now, these summation formulas like this can be pretty difficult to figure out in general, but for certain functions, and y equals x squared is one of them, or for certain types of summations like the sum from 1 to n of I squared, these are known values and they're put in calculus textbooks all over. In the particular book I'm using right now, these formulas are given on page 262. So if you look at page 262, what you'll show here is that the sum from k equals 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 all over 6. And again, this is given on page 262 of our textbook here. So it doesn't matter, I called it I, they called it K in the book. That doesn't matter. These are just names. So that means that within this summation work that I have, this right here can be written n times n plus 1 times 2n plus 1 over 6. So this is going to equal 64 over n cubed times, and again, this thing in red is equal to n times n plus 1 times 2n plus 1 all over 6. And again, I'm applying this formula here for summations on page 262 of our textbook here. All right. Now, there are very limited formulas for this. We only have formulas to do sum over k, k squared, and k cubed, and we'll talk about other methods for doing the summations in another problem. All right, also keep in mind that this formula is just an estimate. The total area is approximately equal to the sum. Now what we're going to do is we're going to make the area exact by taking the limit as n goes to infinity. If we take the limit as n goes to infinity of this expression, and rather than redoing it, I'm just going to we take the limit as n goes to infinity of this expression, the estimate becomes exact. I'm going to save that. All right, I need to get rid of some work here and talk about how to get the limit done. All right, so equals. Now, we got limit as n goes to infinity of 64 over 6. Now, if we multiply this out in the top, we are going to get, whoops, and that's n 64 over 6. Then there's an n cubed in the bottom. And the top, this is going to be 2n cubed plus 3n squared, whoops, 2 and 1, yep, plus n. So what I did is I FOILed this and then multiplied everything by n. And when we take this limit as n goes to infinity, just do it term by term. This limit here is 2. This one is 0, and this one is also 0 because 3n squared over n cubed is 3 over n as n goes to infinity. That goes to 0. N over n cubed is 1 over n squared as n goes to infinity, so that's 0. So when we take the limit of all of this, the 2 is the only thing that survives. So this is equal to 64 times 2 over 6. Or in other words, 64 thirds. Now, I'm going to take a moment here and just look this over and pause it and check it for correctness.